Hello, and welcome to the lecture on 10.2. Today we're going to talk about linear equations in several variables. Now this section is going to be very similar to section 1 because it's basically the same topics that we're going to cover. The only difference is that in this section we're talking about more than two variables for the most part. Let's start with the definition. A linear equation in n variables is an equation of the form a sub 1, x sub 1, plus a sub 2, x sub 2, plus a sub 3, x sub 3, all the way up to a sub n, x sub n equals c. Now note that these are different variables. X sub 1, x sub 2, all the way up to x sub n are different variables. It would be like x, y, z, w, using all the different letters of the alphabet, except n could be more than 26, in which case we would be out of letters. That's why we number them. This is not x to the first power and x to the second power and so on. This is x sub 1, the first variable, x sub 2, the second variable, and so on. Where a sub 1, a sub 2, all the way up to a sub n are real numbers, and x sub 1, all the way up to x sub n are the variables. I'm going to show you an example of what these look like. Most of the time we're only talking about three variables, so we use x, y, and z. Here, we have a sub 1x plus a sub 2y is equal to c. This is what we talked about in 10.1. We might also have something that looks like a sub 1x plus a sub 2y plus a sub 3z is equal to c. And here, this is basically what we're going to talk about in this section, where we have three variables. But it is also possible to have more than three variables. For instance, a sub 1x plus a sub 2y plus a sub 3z plus a sub 4w is equal to c. We could go to as many variables as we want, but generally we stop at 3 to 4 variables because the systems of equations become very, very large if we go beyond this. The next topic I want to cover is solving a linear system. Let's suppose that we have a system of linear equations. a1x plus a2y plus a3z is equal to a4, b1x plus b2y plus b3z is equal to 4, c1x plus c2y plus c is equal to c4. Now let me show you the triangular form of a system of linear equations. So suppose instead that we had a system that looked like this. a1x plus a2y plus a3z is equal to a4, b2y plus b3z is equal to b4, and c3z is equal to c4. Now this system here is very, very easy to solve. In this system, we have three equations, three unknowns. All of these equations are using x, y, and z as their variables. It just so happens that you have a 0 for your x coefficient in this equation, and you have a 0 for your x and y coefficients in this equation. So here, we have one equation, one unknown, so we can solve for z very easily in this equation. Once we have z solved for, we can just plug it in here and solve for y. Because we know what z is, it would be a single equation and a single unknown again. Then once we have y and z, we can plug them both in here and solve for x. This is all called back substitution, and we've done it several times in the last section where it's the last step of solving a system of linear equations. And I'll show you what I mean by this. Let's do an example here. Solve the system. So suppose we have the equations 1, x plus 2y minus z is equal to 2. 2, y minus 3z is equal to negative 1. And 3, 2z is equal to 2. Now all we need to do is solve for x, y, and z. So first, we solve for z in this last equation. 2z equals 2. We divide both sides by 2. This implies that z is equal to 1. Then we back substitute into the equation 2. We do equation 2 such that z is equal to 1, and we get y minus 3 times 1 is equal to negative 1. We add our 3 over, and we get y is equal to 2. So now I have z is equal to 1, y is equal to 2. I just need to figure out what x is. But since we know what z and y are, we can plug them both in. Y is equal to 2, z is equal to 1, and we plug them both into equation 1, and we get x plus 2 times 2 minus 1 is equal to 2. Try one. Solve the system. 2x minus y plus z is equal to 5. Y minus 2z is equal to negative 2. And 12z is equal to 12. Definition. Equivalent systems are systems with the same solution set. Operations that yield an equivalent system. So I'm going to go over these 3 operations in a second. But I want to discuss for a second why we're defining equivalent systems. So, as we've noticed, a triangular system is very easy to solve. We can figure out what one of the variables is, plug it in, we can figure out what the next variable is, plug them both into the last one, and we can figure out what that third one is. So it would be really nice if in a non-triangular system, we could make it equivalent to a triangular system, because then we would be able to easily solve it. Well, that's what we're going to try to do here. And the reason we need equivalent systems is we need to know what type of operations will allow us to put it in a different form. So we'll have a system, we want to change the form of this system to be a triangular system, and then solve that triangular system that will give us the same exact solution set. That's the whole point here. So the first operation, add a non-zero multiple of one equation to another. 2. Multiply an equation by a non-zero constant. And 3. Interchange the positions of 2 equations. Now this third one seems a little bit too obvious to be a rule. That's because we're going to talk about this one more later on when we get into some more formatting of these types of systems. So 3 is sort of irrelevant. We're not really going to use it a lot when we're talking about our systems, but 1 and 2 are very important. This is a lot like what we've done with the elimination method, when we take one of the equations, multiply it by a number, and then add them together or subtract them to eliminate a variable. That's basically what we're talking about with number 1. Number 2, just multiplying an equation by a non-zero constant. Now this means that we can take both sides of an equation and multiply it by a number. We've also done this, but in a way that was to get us to an end goal. It was less impactful on the problem. I do want to note that using these operations is called Gaussian elimination. Let's go ahead and do an example. Solve the system. Equation 1, 2x minus 3y plus z is equal to 11. 2, x minus y plus 2z is equal to 7. And 3, 2x plus y minus 3z is equal to 7 as well. All right, so we want to remember these rules. We can take one equation, multiply it by a number, and add it to another equation. You can actually take both equations, multiply it by numbers, and then add them together. Or we can multiply an equation by a non-zero constant. So what I'm going to do first is use the elimination method. Right, now what I want to do is I want to eliminate the x variable so that I can have 2 equations and 2 unknowns. Here, I'm going to take equation 1 and subtract equation 3. So we do 2x minus 2x. That's 0x. Negative 3y minus y would be negative 4y. Z minus 3z is 4z. And 11 minus 7 is 4. Next, what I want to do is use a different pair of equations. So I used equation 1 and 3 already. Now I either want to use equation 1 and 2 or 2 and 3. It actually doesn't matter which ones you use. Again, the solution set will be the same because we're yielding an equivalent system. So I'm going to take equation 2 and multiply it by 2 and then subtract. So it's going to be equation 1 minus 2 times equation 2. Let me show you what I'm doing down here. So I take 2x, this is equation 1, minus 3y plus z is equal to 11. And 2 times equation 2 is 2x minus 2y plus 4z is equal to 14. And then I'm subtracting. So 2x minus 2x, negative 3y minus negative 2y is going to give me negative y. Z minus 4z, z minus 4z would be negative 3z. And 11 minus 14 is negative 3. So notice here that I have 2 equations and 2 unknowns. So previously I had 3 equations and 3 unknowns. Now I have 2 equations and 2 unknowns. I've completely eliminated the x variable. Now the next thing I want to do is eliminate either y or z. We're going to end up eliminating y. First, I want to take equation 4, and I want to divide it by 4. So 1/4 times equation 4 give me 1/4 of negative 4y will be negative y. 1/4 of 4z is z, and 1/4 of 4 is 1. Then I'm going to subtract up. So I'm going to take this equation and subtract this equation. We do 1/4 of equation 4 minus equation 5. So I take negative y, subtract negative y. I get 0. Z minus negative 3z is 4z, and 1 minus negative 3 is 4. Notice I have this equation, this equation, this equation, and any one of these 3 equations is a triangular system. Now this triangular system will yield the exact same solution set because so far we've only followed these steps. I've only added a non-zero multiple of one equation to another in the form of either multiplying by 1 or just and subtracting, so 1 minus 3, or taking an actual multiple of one of the equations, 2 times 2, and doing equation 1 minus 2 times another equation. So these yield an equivalent system. I have 4z is equal to 4. This means that z is equal to 1. Then I can back substitute here. So equation 5, such that z is equal to 1, will give me negative y minus 3 times 1 is equal to negative 3. So I have a negative 3, and I add 3 to both sides, and I have negative y is equal to 0, so y is equal to 0. Now that I know y and z, I can just plug them both into any one of these equations and figure out what x is. So I'm going to take equation 1, plug in z is equal to 1, and y is equal to 0, and solve. So we take equation 1, 2x minus 3 times 0, plus z is equal to 1, so we have a 1 here, is equal to 11. 3 times 0 is 0, so I subtract 1. I get 2x is equal to 10. This means then that x is equal to 5. So our solution is 5, 0, 1. Now remember, it comes as an ordered pair. In this case, an ordered triple, because we have 3 variables instead. This would be a 3-dimensional coordinate, and we'll talk about the number of solutions in a second, but just know that this is a 3-dimensional coordinate in the x, y, z coordinates. Try one. Solve the system. 2x plus y plus 2z is equal to 9. X minus z is equal to 0. And 2x minus 3y plus z is equal to 3. Basically, you'll do the same exact process. You can also do substitution instead. The trouble with substitution is you'd have to solve for one of the variables and plug it into 2 equations. And that will eliminate one of the variables, and then you do that again after you have a system of 2 equations, 2 unknowns. So let's suppose that I solve for x in this equation and plug it into equation 1 and 3. I'll end up with a system like this, not these exact numbers, but like this, where I have 2 equations, 2 unknowns. The 2 unknowns would be z and y, and then I would have to do substitution again. So in this case, I would solve for y and plug it into this equation, and then I have a single equation with a single unknown. You solve for that single unknown and then back substitute like previously. The next topic I want to cover is the number of solutions in a linear system. For a system of linear equations, exactly one of the following is true. 1, the system has exactly one solution. 2, the system has no solution. 3, the system has infinitely many solutions. So recall that these are actually from the last section as well. Just like a system with just 2 variables, a system with many variables has the same solution sets. You can have either one solution, no solution, or infinitely many solutions. Also recall, a system is called inconsistent if it has no solution. A system is called dependent if it has infinitely many solutions. Note, a linear equation with 3 variables is a plane in 3-dimensional space. Also note, the intersection of 2 planes in 3-dimensional space is a line. Let me show you 3 different examples of these. One solution is pretty much always the same. This would be one solution, and the solution would be where all 3 of the planes intersect, right here in the middle. So here this would be infinitely many solutions, which means that this is actually called a dependent system. And finally, one with no solutions. Now there's multiple versions of this. If none of the 3 planes intersect, then obviously you have a no solution case. But here's another more creative example of when you have a no solution case. So when you have 3 planes like this where they intersect each other but not all at a single point, then you have no solution. Now this no solution is also called inconsistent. So I want you to notice that here all of the planes intersect each other, but there is no mutually intersection point. Now here, all 3 planes intersect along this line. You have infinitely many solutions, and all of those solutions lie on this line right here. Do a couple of examples and see sort of how this works. Solve the system. Equation 1 is x plus y plus z is equal to 4. Equation 2, 2x minus y plus z is equal to 1. And the third equation is x minus 2y is equal to negative 1. Okay, so let's start by doing the elimination method again. We're going to do 2 times equation 1 minus equation 2. So if you don't remember, what that means is we take 2 times equation 1, and that would be 2x plus 2y plus 2z is equal to 8. Multiply everything by 2. And then, of course, equation 2 is this equation here, and I'm going to subtract. So I take 2x minus 2x is 0. 2y minus a negative y is 3y. And 2z minus z is just z. And I have 8 minus 1 is 7. Now, I'm going to do equation 1 minus equation 3. X minus x is 0. Y minus 2y is 3y. Z minus nothing is just z. And 4 minus a negative 1 is 5. Notice that we have the same equation, 3y plus z, 3y plus z, but we have different solutions over on the right. What this means is that these two lines in 2 dimensions are going to be parallel. So if we subtract these, we would get 0 is equal to 2. And this is never true, right? For any x, y, and z, 0 is never equal to 2. What this means is that there is no solution. All right, now let's do an example with infinitely many solutions. Because these two are actually pretty complicated. Because the infinitely many solutions, I think, is infinitely more complicated than the no solution case, pun intended. So we're going to do the same thing, solve the system. Equation 1, 2x plus y plus 2z is equal to 5. 2, x plus 2y minus z is equal to 2. And 3, 3x plus 3y plus z is equal to 7. Now this is going to come out to infinitely many solutions, but I want to show you how we solve it, because it'll look very similar to the previous example up until we get an equation that doesn't ever work. In our case, the equation will always work. All right. So first things first is I'm going to do equation 1 minus 2 times equation 2. So I need to look at what 2 times equation 2 is. 2 times equation 2 will be 2x plus 4y minus 2z is equal to 4. Now I do equation 1 minus equation 2, 2 times equation 2. The 2x minus 2x is 0. Y minus 4y is negative 3y. And 2z minus a negative 2z is 4z. And then we have 5 minus 4 is 1. Negative 3y plus 4z is equal to 1. Now we do the same thing for equation 1 and 3. But this time, I need to multiply equation 1 by 3 and equation 3 by 2. So we do 3 times equation 1 minus 2 times equation 3. Let's go ahead and write those out. 3 times equation 1 will be 6x plus 3y plus 6z is equal to 15. And 2 times equation 3 is going to be 6x plus 6y plus 2z is equal to 14. Now we subtract this equation minus this equation. 6x minus 6x is 0. 3y minus 6y is negative 3y. 6z minus 2z is 4z. And 15 minus 14 is 1. So notice that we have identical equations here. Identical. So if we try to eliminate another variable, we would end up subtracting and we would get 0 is equal to 0. An always true equation, no matter what x, y, and z are, this equation is true. This means that we have infinitely many solutions. Now this one in particular is a bit tricky because we're only going to have a single variable in our answer. if you remember from last section, our solution came out to have t's in it. We had an ordered pair, but each coordinate in the ordered pair had a t in it. We're going to do the same thing here. So now you see that we have a single equation and two unknowns. So what I'm going to do is say let z equal t. Once we let z equal t, then we can solve for y in terms of t. So we'll have 3y, call this equation 4 and equation 5. So doesn't matter. Equation 4 and 5 are equal, so it doesn't really matter. We'll have negative 3y, so this will be equation 4, plus 4 times t is equal to 1. Add the 3y over, subtract the 1, so we have 4t minus 1 is equal to 3y, and then we can say that y is equal to 4t minus 1 all divided by 3 is y. We already know what z is because we set z equal to t, so we know what z is. And now I just need to solve for x. I'm going to use equation 2 because x doesn't have a coefficient. We say x plus 2 times y, but our y is 4t minus 1 minus z, and z is t, remember? Now, your solution will change based on which variable you set equal to t. So if we set x equal to t, if you eliminated a different variable and you set x equal to t, then you're going to get a different solution than me. But if you use the same variable, set z equal to t, then you should get the same solution. So x plus 8t minus 2 all divided by 3 minus t is equal to 2. Find a common denominator so that we can combine these. X plus 8t minus 2 over 3 minus 3t divided by 3. So we have 8t minus 3t. X plus 5t minus 2 over 3 is equal to 2. And if we just subtract this entire piece over, we'll get x is equal to 2 minus 5t minus 2 all over 3 here. And this is okay. So now we've solved for our x, our y, and our z. And our solution is x in the first coordinate, obviously, 2 minus 5t minus 2 over 3. Y in the second slot, 4t minus 1 over 3. And z in the third slot, which is just t. This will be your solution. Now, again, if I set t equal to something, it will be a solution to this system. Let's let t equal 1. And I want to show you one point in the infinitely many points that is a solution to this equation. Okay, so if we let t equals 1, we get 2 minus 5 minus 2 over 3, 4 minus 1 over 3, and 1. Just plugging in 1 for t. So 5 times 1 would be 5 minus 2. So we'd have 3 divided by 3 here, which is 1. So 2 minus 1 is a 1. 4 minus 1 divided by 3 is also 1. And z is 1 as well. So this would be a specific point that is a solution to this case. Now, when you actually write an answer, the infinitely many solution case, it'll look like this. This is just one specific point that's included in this set of points that I want to show you works for this particular system. So now if we plug in 1 for x, y, and z, we have 2 plus 1 plus 2 is 5. 1 plus 2 minus 1 is 2. 3 plus 3 plus 1 is 7. And then if you do 4, or I'm going to do negative 2 instead, just to keep with so that we get whole numbers, we would have 2 minus This would be a negative 10 minus 2 is negative 12 over 3. And then this would be negative 8 minus 1 is negative 9 over 3. And then negative 2 here. So we would have 2 plus 4 is 6. Negative 3, negative 2 is another solution. I'm not going to check that one, but feel free to if you want to. Try one. Solve the system. X plus 2y plus 2z is equal to 1. X plus 5y plus z is equal to negative 2. X minus y plus 3z is equal to 5. All right, the next thing I want to talk about is modeling using linear systems. Note, this is an extension of modeling with two variables. Last section we talked about modeling with two variables. This is just an extension of that, that's all. Let's go ahead and do an example. Sid's Parlor serves 3 drinks that contain Bonnet & booze, Java juice, and Lothal spice brew. Each drink contains the amount of each ingredient outlined below in the table. On a particular day, Sid's Parlor used 820 ounces of Bonnet & booze, 690 ounces of Java juice, and 450 ounces of Lothal spice brew. How many of each drink were sold that day? Okay, so we're going to use this chart to set up our system of equations. Now again, we need to figure out what the question is asking for. So we look at the last sentence. How many of each drink were sold? So X is the number of drink 1 that were sold. Y will be the number of drink 2 that was sold. And Z, of course, is going to be the number of drink 3 sold. So here, 8x ounces of Bonnet & booze used in just drink 1. So Sid's Parlor sold a certain number of drink 1s, that's X. However many of this type of drink. Right? And each one of the drinks that they sold from drink 1 has 8 ounces of Bonnet & booze in it. That means that 8x will be the total number of ounces that we used to make drink 1 and sold it. 6y will be the same thing. The ounces of Bonnet & booze, but for drink 2. Again, we sold a certain number of drink 2s, and each of those drinks that we sold had 6 ounces of Bonnet & booze. So that 6 times y is the total number of ounces of Bonnet & booze that we used only on drink 2s. And then 2z is the ounces of Bonnet & booze for drink 3. Now notice, we used 820 total ounces of Bonnet & booze. So these 3 values should add up to 820. We do that for Java juice and Lothal spice brew because we have those amounts as well. So we get 8x plus 6y plus 2z is equal to 820. 3x plus 5y plus 8z is going to equal 690. And 3x plus 3y plus 4z is going to equal 450. And this is our system. I think eliminating z will probably be the easiest. That way we don't have to deal with 3s and 8s. 3 is not a factor of 8. 2 is a factor of 8, and 4 is a factor of 8, so I feel like this would be the best one to eliminate first. So we'll eliminate z. And I need two equations that eliminate z. So then I'll have two equations with just x's and y's in it, i.e. two unknowns. So we do 4 times equation 1 minus equation 2. 4 times 8 is 32. 32 minus 3 is 29. 4 times 6 is 24. 24 minus 5 is 19. 4 times 2 is 8. 8 minus 8 is 0. And 4 times 820 minus 690. 3,280 minus 690. We get 2590. Okay, so we have an equation with just x's and y's. And then we use equation 1 and equation 3. So 2 times equation 1 minus equation 3. 2 times 8 is 16. 16 minus 3 is 13. 2 times 6 is 12. 12 minus 3 is 9. 2 times 2 is 4. 4 minus 4 is 0. And then 2 times 820 minus 450 is 1190. Oof, these numbers are rough. I think we eliminate y next. So I need to multiply all this equation 4 and call this equation 5. So we need to do 9 times equation 4 minus 19 times equation 5. This is brutal. 9 times 29 minus 19 times 13. And we get 14. 14x. And again, 9 times 19 minus 19 times 9 will give us 0. Then 9 times 2590 minus 19 times 1190. And we get 700. Then if we solve for x, we get x is equal to 50. Plug in 50 for equation 5. So we do 5 such that x is equal to 50. We do 13 times 50 will be 650 plus 9y is equal to 1190. And we solve for y. So 650 or 1190 minus 650 brings us to 540 equal to 9y. And if we divide by 9, we get that y is equal to 60. And then the last thing we need to do is take our x and our y and plug it into any one of these equations. And we'll do equation, I think equation 3 will probably be easiest. 3 such that x is equal to 50, y is equal to 60, and we get 3 times 50 plus 3 times 60 plus 4z equals 450. $150 plus 180 plus 4z is equal to 450. 4z will equal 120, and this means that z is equal to 30. So in total, we sold 50 drink 1s, 60 drink 2s, and 30 drink 3s. Our solution, 50 drink 1, 60 drink 2, and 30 drink 3s. Now, just like last section, we set up the problem using the variables from the last question. We write out what we know based on the operation that we use. 8 times x is the number of ounces in drink 1 and such like that. And then we write the equations for each. This would be the total ounces from drink 1 sold, the total ounces from drink 2 sold, and the total ounces from drink 3 sold. And we compare that with the amount of ounces that we used in totality for each ingredient. And then you simply solve the equation. And I know simply is doing a lot of heavy lifting there. This problem is actually particularly difficult because of the numbers. The numbers are pretty large. All right, that's going to be it for today. I will see you all at the next lecture.